All right, I wanted to make sure that I came up with a video solution for all the problems in your paper 2-3 review. So I'm going to just dive in and get started here. And again, my goal here is to kind of outline thoughts that I have as a teacher even before I solve the problem. So just the color scheme I'm going to use is these are teacher thoughts. And then I will also invoke what I call data booklet equations. And then these are like memorized equations, okay? And that's kind of how we're going to do this. So that's really going to be the idea here. So when I actually approach this problem here and they tell me that there is a question about circular motion, I immediately think to myself, let's grab equations. And for me, when I look at circular motion, I want to remember that centripetal acceleration is v squared divided by the radius of the circle. I also want to recall that the net force on an object is its mass times its acceleration. And just in case, I may not need it, but I always like to remember that the speed going around a circle is its circumference divided by the time. So let's now go ahead, and what I want to do is label my letters just to be clear. So constant speed of v and a radius r of 100 meters. Now, one thing I want to say, I don't think that this question pops up in this particular paper 3 question, but I do want to address one small point here. You see where it says constant speed here? I want to be clear on one thing, okay? And I'm just going to write it down here. Note, not in equilibrium. Okay, forces do not balance here. Okay, forces don't balance. So F net is not equal to 0. Forces don't balance. That's one of those things about centripetal or circular motion, is that if you're going in a circle, your direction is changing. And if your direction is changing, then you're not at a constant velocity, because constant velocity requires not only the same speed, but you have to continue in the same direction. So just please keep that in mind. Now, when they ask us to calculate the acceleration of the car, let's keep this simple. The centripetal acceleration is going to be the v squared over r that they give me. That's going to be 20 squared divided by this radius of 100. So that's going to be 400 divided by 100. And that gives me an acceleration of 4 meters per second squared. Now, then they ask, this is the most common this question right here. Whenever I see this, this is just such a common question. And the answer is always towards the center of the circle. That's the whole point of circular forces. So I know I wrote that in orange just to kind of capture the teacher thought, but I want to write the actual answer here. So towards the center of the circle. Now, I'm just going to follow up here. And you know what? I'm going to write one more little color code just to kind of guide me. If I write something in red, this is an incorrect idea. Okay. Now, here's an incorrect idea that I see students make. So, students often say, well, the centripetal force. That basically is saying the force that makes it go in a circle is the force that makes it accelerate. You need to name a specific cause, so this is not right. So to be clear, okay, you need an actual physical cause of the force. So what I mean by that is gravity is causal, friction is causal, Normal force is causal. Those are real pushes and pulls. So for these, I need the actual source of the push or the pull. Okay, if you say centripetal force, that's the effect. When you say centripetal force, you're saying, I'm not sure what the force is, but I know it makes it move in a circle. So that is not correct. The force that makes this car actually go in a circle as it goes around the road. So, I mean, what have we got? We've got gravity force, but why would gravity make something move in a circle? It makes it go in a circle. Or it makes it fall. Gravity makes things fall. We've got the normal force on the car, right? So we've got normal reaction force, we've got gravity, right? What actually makes the car move in a circle? It turns out it's the friction force. In other words, on a slick road, it's harder to take that turn. So this is question number 4, and we'll take a look at question number 5 in the next video.